Welcome to this session on measuring alternating electrical signals. Unlike DC signals that remain steady, alternating signals continuously fluctuate in magnitude and polarity over time. They carry energy in a dynamic form essential for modern systems, from household power to wireless communication. Today, we're going beyond just how to measure AC. We'll discuss why AC behaves the way it does, how measurement tools interpret it, and what we must consider to get meaningful, accurate results. The first question we must ask is, what makes AC measurement fundamentally different from DC? Let's look at the physics. In DC, electrons flow in one direction due to a steady electric field. The voltage and current are time invariant. But in AC, the electric field itself oscillates. This causes electrons to periodically reverse direction, creating a waveform that varies with time, typically sinusoidally. Why sine waves? Because they are solutions to the differential equations governing rotating magnetic fields in generators. This time-varying nature means the instantaneous value changes continuously. The sine flips every half cycle, and the average over one full cycle is 0 for a pure sine wave. So DC instruments can't interpret the net value of AC. They need to be adapted or replaced with AC-specific tools. Let's now break down the three common ways we describe AC signals. We start with instantaneous value. This is the value of the voltage or current at a single point in time. Example, it's like a snapshot, but it doesn't tell you anything about the signal's energy over time. Let's talk about the peak value. This is the maximum positive or negative swing of the waveform. It's critical in overvoltage protection, component ratings, and signal clipping analysis. However, like instantaneous value, it doesn't reflect power. We have another quantity called RMS value, which is the most meaningful for engineering applications. It stands for root mean square. The RMS value is equal to square root of I over time period times the integral of square voltage function over one cycle. Why square it? Because power in resistive loads is proportional to V squared. For a sinusoidal signal, RMS value is equal to peak value divided by square root of 2. This tells you the DC equivalent voltage that would produce the same heating effect in a resistor. Let's now move from the theory of AC measurement to the tools we use, starting with the most common one in your lab or toolbox, the digital multimeter or DMM. Now, not all DMMs are created equal when it comes to AC measurement. There are two main types, and the difference lies in how they calculate the RMS value. Most basic or inexpensive DMMs are average responding. Here's how they work. Internally, they rectify the AC signal. Then they compute the average value of the resulting waveform. Finally, they scale this average by a constant factor, like 1.11 for sine waves, to estimate the RMS value. That works only if the waveform is a pure sine wave. Why? Because the relationship between average value and RMS value depends on the waveform shape. But if you apply a square wave or a distorted signal, that 1.11 factor no longer holds true. On the other hand, true RMS DMMs take a more physics-based approach. They digitally sample the signal at multiple time points, square each sample, compute the average of the squared samples, then take the square root. This directly implements the true RMS formula. Because it works from first principles, it doesn't care what shape the waveform is. Now let's talk about one of the most powerful tools in any electrical engineer's arsenal, the oscilloscope. At its core, the oscilloscope is a time domain visualization tool. That means it doesn't just give you a number like a multimeter. It shows you how your voltage or current changes over time. It opens a window into the dynamic behavior of electrical signals. Why use an oscilloscope? In AC and signal systems, we care not just about how much, but when the signal rises, falls, repeats, or shifts relative to another. These time-based properties are invisible to a multimeter, but crucial for understanding power systems, communication, or even control logic. An oscilloscope plots voltage or current on the vertical axis against time on the horizontal axis. This reveals the waveform shape and tells us, is it a clean sine wave? Is it a square wave, triangle wave, or noisy? Is there distortion, overshoot, or clipping? For example, if you're testing an amplifier and the waveform flattens at the peaks, that's clipping. Once you see the waveform, you can use cursor tools or automatic measurement functions to determine peak voltage or peak-to-peak voltage or RMS voltage, By measuring the period t of the waveform, you can also calculate the frequency f. Scopes often offer a time-based knob that lets you zoom in or out in time to precisely see where cycles begin and end. Oscilloscopes also help us to view phase relationships between two signals. This is where the dual-channel capability shines. Let's say you're analyzing a voltage across a capacitor and current through an inductor. You can connect channel 1 to measure the voltage and channel 2 to measure the current. Now observe how the waveforms align in time. Are the peaks of one delayed compared to the other? This delay is called phase shift, and it's critical in AC power and reactive systems. Now let's talk about some practical tips. Always make sure your oscilloscope has bandwidth higher than 5 times the highest signal frequency to avoid distortion, and you have to have high sampling rate to avoid aliasing. Otherwise, you may miss fast transients or underestimate the true peak and frequency content. Let's now turn our attention to a tool that does for frequency what the oscilloscope does for time. If the oscilloscope gives us a movie of the signal as it changes over time, the spectrum analyzer gives us the DNA of the signal, revealing exactly what frequencies are present and in what proportion. This is essential for engineers working with communication systems, audio electronics, radio frequency systems, and signal integrity analysis. Think of electrical signals like music. A single note is a pure sine wave. But when you play a chord or an entire song, it's a complex mixture of multiple frequencies occurring at once. Now imagine trying to understand that song just by watching how the air pressure varies with time. That's what the oscilloscope does. But if you want to analyze which musical notes are present, how loud they are, and whether there's noise or distortion, you need to break it into its frequency components. This is what a spectrum analyzer does. A perfect analogy is a prism. When white light passes through a prism, it's split into its constituent colors: red, orange, yellow, and so on. Likewise, when a time domain signal passes through a fast Fourier transform, the mathematical engine inside the spectrum analyzer, it gets split into all the frequencies that make it up. So, just as a prism tells us what colors are present in a light beam, a spectrum analyzer tells us what frequencies are present in an electrical signal. Inside the spectrum analyzer, your time domain signal is first digitized, converted from analog voltage to digital samples using an ADC. Then, it undergoes a fast Fourier transform that breaks down the waveform into a sum of sine waves at different frequencies. The output is displayed as a graph where horizontal axis frequency and vertical axis is amplitude, often in decibels. You can identify the dominant frequency component, or if a signal is not a pure sine wave, it contains multiple harmonics. These appear as peaks at integer multiples of the fundamental frequency. In AM or FM signals, the spectrum analyzer can show sidebands frequencies that represent the information content being transmitted. This is how we analyze modulated signals in radio, TV, or mobile communications. Also, if there's unwanted energy in the spectrum due to EMI switching circuits or crosstalk, it will appear as broadband noise or unexpected spikes. You can visually spot sources of interference and determine whether they're narrowband or broadband. Let's now take a step beyond handheld tools like multimeters and oscilloscopes. In high-accuracy systems, especially in industrial control and power analysis applications, we need more robust and precise solutions. These systems go far beyond just showing voltage. They give us real-time, accurate, and dynamic measurements, even under complex signal conditions like harmonics, switching transients, or distorted waveforms. Such setups typically involve 3 main building blocks. Let's begin with the precision rectifier, also known as the superdiode. Unlike ordinary diodes, which suffer from a 0.6 volt to 0.7 volt voltage drop, a precision rectifier uses an op-amp with diodes in a feedback configuration. The setup eliminates the diode voltage drop, enabling accurate rectification even for low-level AC signals, such as in microvolt range, biomedical instrumentation, or sensitive sensor circuits. A diode alone doesn't conduct until the signal exceeds its threshold. That means if you're measuring a 0.4 volt sine wave, a traditional diode clipper would completely miss it. But a precision rectifier activates immediately, preserving the waveform for accurate downstream processing. Once rectified, the signal is still pulsing. It's no longer AC, but it's not yet stable DC either. It's full of ripple. To stabilize it, we pass the signal through a low-pass filter, which typically is an RC or active filter. This filter removes high-frequency ripple, leaving behind a steady voltage that represents the average or RMS value of the original signal. Think of this like filling a bucket with pulses of water. Without a filter, the water level rises and falls with each squirt. A filter is like a sponge inside the bucket. It absorbs fast surges and delivers a calm average level. After rectification and filtering, we now have a clean DC representation of an AC signal. But to process it digitally, say in a microcontroller or DSP, we need an ADC to digitize this analog value. Most modern RMS measurement systems use a sampling-based ADC, often integrated with DSP algorithms that calculate true RMS value, frequency, phase angle, and total harmonic distortion. Remember, in modern instruments, the RMS value is no longer estimated by analog circuitry alone. It's often digitally computed by squaring each sample, averaging them, and taking the square root. This matches the mathematical RMS definition exactly, even for distorted waveforms. Now, where are these high-accuracy systems used? These building blocks form the core of precision AC measurement systems in the following key areas. Number one is power quality analysis. When you want to know more than just how much voltage, you want to know about harmonics, flicker, voltage sag, and power factor, you need high-accuracy systems built on the blocks we discussed. The second one is motor control and drives. Induction and brushless DC motors rely on sensor feedback loops to adjust torque, speed, and voltage dynamically. Measuring AC currents or voltages accurately in real time is mission critical for closed-loop performance. Third is PWM signal characterization. PWM, or pulse width modulation, is the workhorse of modern electronics used in everything from LED dimmers to Tesla's inverter. But PWM signals are not pure sine waves. They're full of sharp edges, switching harmonics, and noise. A traditional RMS meter fails here, but precision rectifier plus filter plus ADC setups can decode the effective power hidden inside these pulses. That's what matters for thermal modeling, energy transfer, and compliance testing. In AC systems, we're not just interested in how big the voltage or current is. We also care about when it rises and falls and how fast it oscillates. These two timing-related properties are captured by frequency and phase. Let's break them down carefully. Frequency is defined as how fast the signal repeats. Frequency, denoted by F, tells us how many times per second a waveform completes one full cycle. Mathematically, F is equal to 1 over signal period. Think of AC like a pendulum. High frequency is when pendulum swinging back and forth very rapidly. Low frequency is when pendulum swinging slowly. In an electrical conductor, higher frequency means the electric field is changing faster, causing electrons to accelerate, stop, and reverse direction more rapidly. Now, why frequency matters? Most electrical devices are designed for fixed frequencies. A significant deviation can cause motors to run too fast or too slow, transformers to overheat, or clocks to lose accuracy. Also, in RLC circuits, frequency determines impedance and resonance. Tuning a circuit to the wrong frequency can cause poor filtering or excessive power loss. In addition to those, in radio and Wi-Fi, specific frequencies are allocated by regulation. A wrong frequency means interference or even illegal operation. Now that we've discussed how to measure alternating signals, let's talk about something just as important. What can go wrong when you're trying to make those measurements? Even with the right tools, incorrect setup or misunderstanding of instrument limitations can lead to significant measurement errors, wrong diagnostics, and even equipment damage. Let's examine the most common pitfalls in AC measurements. First, let's talk about loading effects. When you connect a measurement device such as a probe, oscilloscope, or multimeter, you are not just observing the circuit. You are becoming part of the circuit. Every measurement tool has input impedance, meaning it draws some current from the node you're probing. This loads the circuit and can affect the very quantity you're trying to measure. Remember, always use high impedance probes for voltage measurement, typically 10 mega ohm or more. For sensitive measurements, consider buffer amplifiers to isolate the probe from the circuit. Every measuring device also has a bandwidth limit, the maximum frequency it can accurately track. If the frequency of your signal or its harmonics is higher than the instrument's bandwidth, you will see attenuated, distorted, or delayed measurements. You should always check that your scope or meter has bandwidth at least 5 times the highest frequency component, including harmonics if it's a square or PWM waveform. Another aspect is that passive oscilloscope probes use an internal voltage divider to reduce the signal amplitude. But these dividers rely on both resistors and capacitors. If the capacitive ratio is not properly balanced, the probe won't respond accurately to fast edges. It either overshoots or rounds off the waveform. So before every lab or measurement session, use the probe calibration output on your oscilloscope to adjust the probe's compensation screw. Make sure a square wave looks square with flat tops and vertical edges. Please note that many handheld multimeters are average responding RMS scaled. This means they assume you are measuring a perfect sine wave and apply a fixed conversion factor. But if your signal is not a sine wave, for example, a square wave, triangle, or distorted waveform, this assumption breaks down. So you should use a true RMS meter if your signal is not a sine wave, or you are dealing with PWM, audio, power electronics, or mixed harmonics. In DC circuits, power is straightforward. P is equal to V times I. The voltage and current are constant, and all power delivered to the load is real power, doing useful work such as heating, lighting, or mechanical motion. But in AC systems, things are much more nuanced because voltage and current are not always in phase. Energy can flow back and forth between the source and reactive components without being consumed. This gives us three distinct types of power, which are real power, reactive power, and apparent power. Let's break each one down. The real power is the actual work done. It is shown by P, and it's equal to RMS value of voltage times RMS value of current time cosine of the phase angle. Real power is the useful energy per unit time that gets converted to work or heat in the load. In a resistive heater, all of P turns into heat. In a motor, P produces torque. Now, the power factor shows how much of the supplied power is actually doing useful work. A power factor of 1 means 100% efficient energy transfer. The reactive power, on the other hand, is stored and released energy. It is shown by Q, and it's equal to RMS value of voltage times RMS value of current times sine of the phase angle. Reactive power is the energy that oscillates back and forth between the source and reactive components like inductors and capacitors. Inductors store energy in magnetic fields. Capacitors store energy in electric fields. This energy is not consumed but continuously transferred in and out of the source every half cycle. Apparent power is total supplied power. It is shown by S, and it's equal to RMS value of voltage times RMS value of current. It's the vector sum of real and reactive power. So S square is equal to P square plus Q square, and it's measured in volt amperes. Apparent power is the total power the source must supply to handle both the useful energy transfer and the reactive energy exchange. Even though Q doesn't perform real work, the source must still provide current for it. This increases current stress, cable heating, and transformer loading. Think of the power triangle. The base is real power. The vertical side is reactive power. The hypotenuse is apparent power. The angle between S and P is the phase angle. Small phase angle means better power factor, which is more efficient. Large phase angle means or reactive burden, which is lower efficiency. Improving power factor shrinks Q, reduces S, and lowers transmission losses. But how do we measure these three powers? Real power is measured with wattmeters or true RMS power analyzers. Reactive power is calculated from PS and phase angle or measured with dedicated VR meters. Apparent power is simply V RMS times I RMS. Understanding P, Q, and S is not just academic. It's fundamental to designing efficient systems, selecting proper equipment ratings, and maintaining grid stability. If you only look at RMS voltage and current without considering phase, you're only seeing half the picture.